Hello and welcome to the first video in the series on functional analysis. And for these videos you will need to be familiar with the following concepts from a linear algebra and a real analysis course. Firstly, you need to know what a vector space is. You need to know some basic notions about real analysis, so you need to know about limits, series, sequences, convergence, etc. You'll need to know about linear maps and transformations, and a little bit of knowledge of group theory would be useful as well, but it's not essential. Okay, so let's look at our motivation. So essentially, we want to find out how much of our knowledge of vector spaces extends over to the infinite dimensional vector spaces. Okay, and this will lead us on to the notion of a Hilbert space and eventually a Banach space. Okay, so firstly I'm going to introduce some notation. So I'm going to call it notation. Okay, we're going to call R to the n, okay, it's going to be a set. So it's going to be a set of all vectors, v1, v2, v3, etc., such that each of these v1 up to some vk are all in the real numbers. So all these are real numbers. That's going to be r, I'm going to call it r to the n. Okay. And how do we add two vectors in the form r to the n? Well, firstly, this is going to be a vector space, and you can check that yourself. Okay, and these are going to be our operations defined on our vector space. If I take two vectors v and w, then each component will be just v1 plus w1, and then v2 plus w2, etc. And if I take some scalar in our field, and the field we're going to use is r, then a times v for the scalar is going to be just a times v1 for the first component, a times v2 for the second component, and etc. Okay. And finally, I can define a dot product on r to the n. And that's just going to be, as you're usually familiar with, first component, well, it's going to be a number, actually, a scalar, so it's going to be v1 times w1 plus v2 times w2, etc. Where I just multiply each of these components. And I'm going to write that as a sum. It's a sum from k is equal to, from k is 1 to infinity, of vk times wk. And the first question you may ask is, when does this converge? Because this may not always converge. Of course, if each entry is bigger than 1, then it's not going to converge, is it? So if I take v is equal to 1, 1, 1, etc., and this is going to go on for infinity, it's just going to be the constant vector. Well, I've got 1 in each component, and I've got n multiples of those, okay? Then if I do v dotted with itself, of course, you may be familiar with that being written as the modulus of v squared. Okay, well, that's just going to be the sum from k is equal to, from 1 to infinity, of just 1 squared. And of course, that's going to blow up. That's not going to converge. However, if I take, show another example of where it does converge. If I take v is equal to this vector, I can have 1 in the first component, half in the second, third in the third component, etc. Okay, then v dotted with itself is going to be sum from k equals 1 to infinity of 1 over k squared. Okay, and that, as you may know, is actually pi squared over 6. So that does converge, so I'm happy. Okay, right. So this r to the n, that's going to be a vector space, okay? And we are going to be concentrating now on forms, vectors of the form where I can I can square each of the components, add them all up, and it converges. So they're going to be, that we're going to denote our definition. So here's a definition. The first definition we're going to use. I call this definition number 1, or def. Okay, so L2 of n comma r, that's going to be equal to, it's going to be a set of all vectors v in r to the n, such that if I add up each of the components in v and I square them all this result converges. It's just going to be the set of all vectors where these, I square them all and they converge, or otherwise where they have a finite modulus. Okay, right, fantastic. So let's show this is, the first result we want to show is that this is a vector space. Well, this is clearly a subset of R to the n, which I claimed is a vector space, which you need to show. And secondly, we want to show that this is also a vector space. Okay, so we want to show it's a subspace. So here's going to be our first lemma. So claim is that L2, okay, and R, this is a subspace, of course, of R to the n. Well, to show this, the first claim I need to show is that it's non-empty. Okay, so if U is a subspace, if U is a vector space, I'm trying to show U is a subspace, I need to show that U is not equal to the empty set. Well, how about we take the 0 vector in R to the n? Well, what is the 0 vector? Well, that's just a vector of 0 in each component. Well, of course, well, I know that the sum k is equal to 1 to infinity of 0 squared is just going to be equal to 0. Okay, so that converges. So that's definitely in there, so it's not empty. Secondly, I need to show that if I take a scalar, so if a is in R, I need to show that this implies a times v is in L2, where, of course, v is in L2 as well. Actually, I'm just going to write this over here so it's nice and clear. So how do we show this? Well, this is not too hard to show either. Okay. To show this, I can take my sum. Okay, here's my sum. K is equal to 1 to infinity. And I can add up each of these components. That's a times vk. And I'm going to square each of these. And I want to show that this converges. And of course, this is equal to the square of k is equal to, from 1 to infinity, of a squared times vk squared. And now we can use our properties of the sum to take this outside. This a is going to now take it outside here. Okay, is because it's linear and it's a vector space, so we can use that. Okay, so now we can take this term outside, and of course this converges. Okay, because this is in L2. Okay, if I times it by a scalar a squared, that's going to also be in L2. So this converges. Great. So a times v is also in L2. Okay, and finally, I need to show this. Okay, if I've got two vectors, u and v, both in L2, okay, I need to show that this, the sum, which I can define, w, which is equal to u plus v, is also in L2. I need to show this, and if I can show this, then I'm done. Okay, so let's look at what this is. So, let's firstly consider this, okay? Well, I can take two vectors, and I can rewrite this in a weird form. So I can say wk squared, that's vk squared plus uk squared. And of course, if I expand this, that's just vk squared plus 2 times vk times wk. Sorry, uk, not w. uk plus uk, I'm just expanding it. Okay, but now I can rewrite this as the following: 2 times vk squared plus uk squared. Oh, sorry, I've mixed my u's and v's around, but it still means the same thing. It doesn't matter which way I'm writing it. And I can take off this term. Okay, I can rewrite it as this. And now, here's the key. This term, all of this term here, okay, because this is greater than or equal to 0, because I'm working with the real numbers, all of this is going to be less than or equal to 2 times vk squared plus uk squared, because of course, like I said, this is greater than or equal to 0, the second term. And now I know, again, that this will now tell me that this sum here is now going to be convergent, because I know that when I sum all of this, I'm gonna be use my linearity of my summation, and I can take my 2 out, and I know that because v is in L2, this is going to converge. I know that this is going to converge, and therefore I know the sum's going to converge because they both converge, and I know that 2 times that is also going to converge. So I'm just using the definition of convergent series, okay? And now I am done. So I have proven that L2 and R is a vector space. And in the next few videos, we will be extending on this notion.